Okay, so let's move on with our discussion on combinational circuits, right? So last class we started discussing very briefly the idea of implementing any arbitrary Boolean function, right? Implementing any Boolean function. So the idea here was I have a black box with inputs, let's say A, B, C, A, B, and C, and some output Y. Let's just take one output. So therefore, you write down the truth table for this for 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way to 1, 1, 1. And then you put down the locations where the output will go to zeros and ones, right? This is how you solve the K-map, right? So in summary, you can represent the output as a sum of products. As a sum of products. And what is that? That's basically also known as min terms. Summation of min terms of, let's say, 0, 3, 7, for example. Right? So what does this mean? 0 is A bar, B bar, C bar. 3 is A bar, B, C. And 7 is A, B, C. Okay. Of course, you can simplify this by combining the A plus A bar and make it 1 and all that. But let's not get into that. Let's assume that you have simplified this whole thing and then you have some expression that you want to implement. So what does this sum of products mean, right? I have a min term 0 plus min term maybe 3 plus a min term 7. Each min term is a product of the inputs, some product of the inputs. Like here it is A bar, B bar, C bar, right? Then I have an OR of the other term, A bar, B, C plus A, B, C, right? So there is a product, right? And that's nothing but an AND condition. And there is a sum operation that is being performed here, which is an OR condition. This is the sum. That's why it's called sum of product, SOP, right? The idea is now to take this and implement it in static CMOS logic, okay? So the point is, if I have any arbitrary switch, right, and I put two of these in series, controlled by signals A and B, then the signal X from here will go to the output Y when both A and B are closed, right? So this can be written as Y equals A and B into X. So there is a Boolean operation on A and B, and then it is passing the logic value X to the output Y, right? So similarly, if I have two arbitrary switches which are in parallel, right, and I have input X1 and X2, right, then my output Y would now be A times X1 plus B times X2, right? Now we have two kinds of switches in static CMOS logic that we can use. One is an NMOS transistor and other is a PMOS transistor, right? So what we said last time was, if I have an NMOS transistor like this, right, trying to pass a logic X, then Y will be A, B into X, okay? The only catch here is that we already know that if X were grounded, then there is absolutely no problem. And if the signals A and B go high, which means they go to VDD, then both NMOS transistors will turn on. The zero from here will appear here, and that zero will also percolate to the output Y. No problem. On the other hand, if I connect this to VDD, then what will go through from here to here is what? VDD minus VT, and further from here to here is also VDD minus VT, right? Whereas for 0, it goes to ground, right? And therefore, the problem with using these NMOS switches is it is not equivalent for both logic levels, right? So the conclusion is that the NMOS gate transistors actually NMOS transistors can be used only for pull down logic. It can be used to pull the output low in some cases. Okay. In other cases, the NMOS transistor will not help because they cannot pass a logic 1 fully. You cannot get a rail to rail output with logic 1. Clear? So let's go back now and look at this sum of product term that we had. Let's say ABC plus A bar, B bar, C bar. So what does this thing mean? It means that when any of the minterms become 1, right, then the output is going to go high. And all the switches in each of the minterms is an active high switch, right? So when A equal to 1, B equal to 1 and C equal to 1 implies A, B, C equals 1. This implies Y equal to 1, right? Or if A bar equal to B bar equal to C bar equals 1, this implies A bar, B bar, C bar equals 1, implies Y equal to 1. So the inputs that are going to control these switches are active high inputs. Okay? And when any of these minterms get activated, the output has to go high. Right? Now this active high inputs is not a problem because naturally the NMOS transistor has an active high input. When the input goes high, A goes high, the NMOS transistor will turn on and therefore the switch will turn on basically, right? The only problem is passing this logic 1 to the output when the switches turn on. So the SOP assumes that when any of these minterms go high, the output has to go high, right? Unfortunately, the NMOS transistor cannot pass a logic high, right? Why are we using the NMOS transistor? Because the switches are active high switches here. In this SOP thing, switches are active high switches and therefore we are going to say use NMOS. Unfortunately, you cannot use it to pass a logic high as the SOP normally demands. Therefore, what you have to do is you have to first invert the function if you want to implement any arbitrary Boolean function in static CMOS logic. So let us say I want to implement f of A, B, C. The first step 1, is invert Y, right? You write Y bar equals F bar of A, B, C. And go ahead and implement this F bar logic in and for the NMOS gates first. We look at what we should do for the PMOS in some time, right? Because I want to get the output to go to logic 0 with the NMOS, but only if I invert will the actual logic be correct, right? And that's why static CMOS logic is inverting by nature, right? So you can go ahead and use this idea that I told you here, where if you put two NMOS transistors in series or n NMOS transistors in series, you get a AND condition. If you have an OR condition, then you have to just put them in parallel. Okay, so let us look at an example. I will look at y equals AB plus CD, right? So the first thing I have to do is I'm going to implement y bar first. Y bar is AB plus CD. No, I will actually consider the complement so that it's easy, right? Then y bar will become AB plus CD. Now I have A into B that has to be implemented using NMOS transistors. So what is the, I put two NMOS transistors in series. So A, B. Now I have the C into D now, which has to be implemented. C and B. And these two now should be in parallel. So therefore you short this output and you get output Y. Right? So when A equal to 1, B equal to 1, the output Y is 0. When C equal to 1 and D equal to 1, output Y is 0. Right? What happens in the other cases? In the other 14 combinations, what will the output Y be? Yeah? Yes. Essentially, what is happening is when any of these pull down paths turn on, the output is pulled low and it is held low. Right? So if you look at this, if A and B turn on, this pull down path is activated, the output Y is simply held low as long as A and B are high. If C and D turn on, then this pull down path is activated, right? And the output again is held low as long as C and D are on. Of course, if A, B, C and D are on, then you have two paths, both of them pull it down to 0, right? So I was wrong in saying the other 14 cases because it must be other 13 cases, right? Because A, B, C, D equal to 1 also is 0. What happens in the other case when these conditions are not satisfied is you have a capacitor here, right? Some parasitic capacitance, load capacitance, all of that, right? You have a capacitance here which is storing some value initially based on the previous state. Now suppose the inputs go into one of these other 13 conditions. That means there is no pull down path through any of these. The input is in that kind of a condition, then the output on the capacitor is just held as it is. And this is known as a high impedance state. Why? Because there is a very high impedance from the capacitor output to any of the rails. And therefore the capacitor voltage is supposed to hold its value there for actually till infinity if there is no leakage current, right? Unfortunately, if A and B, for example, they are connected to the real transistors, then there is going to be subthreshold leakage. So then this capacitor will leak out slowly like this. But that is very slow. So for all practical purposes, you can assume that the capacitor will float at that particular value for long enough, right? So A equal to B equal to C equal to D equal to 1, also Y equal to 0. Other conditions. Yeah? Yeah, 1, 1, 0, 0. So, no. Sorry, can you tell me again? AB can be 1, 1 and the 0, 0 of the other thing. Yeah. Okay, so that's right. So, right, okay, let's not get into that. Similar conditions, right? Y equal to 0. Other conditions, output is floating. Okay, you'll hear this term. Or high impedance, in high impedance state, right? And we basically represent this by Z. So typically high impedance means the output is going to float on a capacitor somewhere. Okay, so we'll use this at a later point in our, right? So what have we done now? We had a function f of a b c d. We inverted it. We implemented the pull down stack, right? This basically is the pull down network. Pull down network. Pull down network. Now, what about the pull-up network? In certain other conditions, I want the output to go high, right? So that I have not yet done. So if you take my thing where I inverted, I got f bar of A, B, C, right? Then I now need to do something in order to implement the pull-up stack, right? So what do you do there? Y bar equal to AB plus CD. Right? So if I now complement this, the output that was supposed to go 0 will go high. Right? So now I will write Y equal to Y bar whole bar, which is basically our original function. Right? I'll tell you how to do this in a simpler way in a minute. I'm just showing you formally what has to be done. Now this can be written like this. Use De Morgan's laws. Make all the ands, ors, ands, and pull the complements inside. Right? So it will become A bar plus B bar into C bar plus D bar. Right? So there is no way that any of these combinations can cause the output, the pull-up network also to turn on and the pull-down network to turn on, because we have complemented these two. Right? So there is no pull-down path, or there's no path for the current from VDD to ground in any of the input combinations. Right? By design, that's what has happened. So now we need to go ahead and implement this function in our pull-up network. Okay, this is for the pull-up network. Now remember, I told you that a PMOS transistor, the switch is an active low switch. So if I connect an input A like this, and this is some X, Y, it implies Y will be A bar into X. Because A has to go down to 0, assuming that there's a VDD on some other node, right, which will make it the source. The transistor will turn on and thereby conduct, right? And therefore, this is an active low switch. So when you see an A bar, you actually just need to connect A to that PMOS transistor. Here, look at this. This one, and this one. Right? So what you do for the pull-up network, you are now going to, I have two terms, A bar plus B bar using two PMOS transistors, and that will be a parallel or series combination. It will be a parallel combination, A bar plus B bar. A bar plus B bar. And this is going to go to VDD. Now that is going to be in series with another network, C bar plus D bar. Right? And this is my output Y. So again, here the output Y, when the input combinations allow a path to VDD, right, which could basically be through any of these combinations, right, the complementary combinations of when it would go to 0, the output Y would go to 1, and otherwise it would be in high impedance, because I have not yet connected the pull down network here. I have just connected a pull up network to VDD. So in the other conditions, the output will float. Okay. So the first useful lesson here is when two outputs are floating in a complementary manner, right? When the output is 0 in the pull down network, it goes to 0, otherwise it floats. In exactly those conditions, that guy, pull up network, is going to pull it up to VDD. So therefore, I can tie these two outputs, do a wired OR connection on these two things and get a proper output, right? So to implement this function, Y equal to AB plus CD whole bar. Yeah, that's what I, sorry. Mistake. Thank you. A, B, C, D. You're right. Yeah, this should be a PMOS transistor. Yes, correct. A, B, C, and D. Okay. So now I just put these two pull-up network and pull-down network together. I get my Boolean logic function that I wanted. Okay. So I have A, B, C, D, C and D again. I'm shorting these two. A and B. This function is AB plus CD whole bar. Okay. Now what if I asked you to implement Y equal to AB plus CD? Then you have to invert it, implement this AB plus CD whole bar, and then add an inverter on the path, which of course is just one PMOS NMOS transistor, and you get it.